So this video is on applied optimization, and applied optimization is really just taking what we already know and using the minimums and maximums to optimize a certain thing. Yeah. So anyways, here's the question. So find the dimensions of x and y of a rectangle that of maximum area formed using 3 meters of wire. So the first thing that we have to do when we're given an applied optimization question, and the first step is to make everything one variable. So because the full final, here I'll draw a picture. So for example, we call this x, this is an x, this is y, this is y. So therefore, by looking at that, 2x plus 2y equals 3, because there's 3 meters of wire. So what we want to do to get this all under one variable is I'll multiply both sides by 1/2, which leaves us with x plus y equals 1.5. Therefore, we can solve for y as y equals 1.5 minus x. So now that we have all of this, now that we have this all in one variable, we can write our area as a function of x. So we can write a of x equals 1. The area would be x times y. So it would be x times what we have now as our y, 1.5 minus x, which equals 1.5x minus x squared. So now that we have this equation, our area equation, we can take the derivative of it to find the maximum and minimums. And in this case, we will be looking for the maximum, where that is where the area will be maximized. So to find the derivative, quite simple, prime of x would equal 1.5 minus 2x. We set this to 0 to find critical points, so we get 1.5 equals 2x, therefore x equals 0.75. So now that we have this as a critical point, we're going to want to go ahead and plug this back into the main area equation, which is right here. And so we'll plug in for x as 0.5, so a of 0.75 will equal 1.5 times 0.75 minus 0.75 squared. Now this will come out to 0.625. So based on what we have here, we can see that the optimal x value, well, what we would think would be 0.75, and which makes sense if you think about it, considering this is more of a basic example. But in some more complicated examples, you have to plug in both the beginning and the end of the interval. And now when you think about this question, you have to determine what interval it would be over. So clearly we don't want a negative interval. X cannot be negative. We can't have a negative amount of wire. Therefore, the interval in this case would be, so x is greater than or equal to 0, but also less than or equal to 1.5. Because 1.5 is exactly half of the amount, it's impossible to make a shape with one side being longer than half of what we have, based on what we have written up here as 2x plus 2y equals 3. If x was greater than 1.5, the equation wouldn't work. So now what we're going to do is we want to plug in x as 0 and 1.5 to make sure that this value that we got here is in fact the correct optimization point. So we're going to plug in for 0 and well, that just comes out to 0. And if we plug in for 1.5, that again comes out to 0. So based on what we have here, we can see that the optimization for x, the x value would be 0.75, meaning that therefore x, the optimized x and y values of this will be x, which equals y, which all equals 0.75 meters.